Okay, hello everybody, and welcome back to the 184th meeting of the Acoustical Society of America in Chicago. We have 3 more presenters during our press conference this session. After each, we'll have some time for your questions, so if you're online, please type those into the question box. We're going to start by hearing from Timothy Leighton of the University of Southampton and Andy Petkulescu from the University of Louisiana at Lafayette. They will describe what we could hear on other planets and also what we've heard already. So we're excited to learn more.
Thank you. So I'm talking in advance of a session on the use of sound for exploring other worlds in our solar system on Thursday. And I have to point out the talk I'll be giving is the most trivial talk of all of them in that session. Everybody should really be there to celebrate the fantastic engineering achievements of the Perseverance team, not mine. But I was asked to talk about mine here and why we got interested in sound in space. So I got interested in about the late 90s because in January the 14th, 2005, the Huygens probe would finish its 7-year journey from Earth to Titan, which is seen there in the bottom of the screen, a large moon around Saturn. And when Huygens did its tremendous landing on the surface, it took photographs like this. And it was great. It was an amazing achievement, but it sat there looking out over this dirty plain for 3 hours, and then the batteries ran out. And there were those of us who'd been saying it's possible that on this very cold world there might be brooks, streams, waterfalls, and lakes, not made of water, which would be ice at these temperatures, but made of liquid methane and ethane. And wouldn't it have been marvelous if there was a microphone that could have heard the babbling brook behind it, because the camera couldn't have seen it. So we were trying to make the case that microphones would be a great thing to put on other worlds. But the implication there is we would recognize the sound as a babbling brook. So one thing I did is start computing what it would sound like if you had a babbling brook made of liquid methane and ethane on this incredibly cold world. And it sounded like this. Perfectly recognizable as a babbling brook, and indeed one of the photographs that came down did see what looked like rivulets, at least carved in the solid, going into a lake. So that was 2005, but there were greater implications because sound doesn't just travel through air. A lot of space missions are done because people think about life. We might discover keys of life, and some of us think the greatest chance of discovering life would be at the bottom of the oceans on Jupiter's moon Europa. And people think we might go there, drill through the icy mantle or melt through it, send a submarine down to the floor and find life. But this is a vast sea. Our own Arctic Ocean has a couple of meters ice over a kilometre of water. This is 20 kilometres of ice over 100 kilometres of water. It's a vast sea. The idea of engineering a probe to go down to the bottom of that sea is vast. But sound waves, we know sound waves will travel through water and ice and explore that for us. So there are all sorts of reasons for interested in sound on other worlds. About a couple of years after this, I met Andy, and a year after that, we organised the first of the ASA sessions in Paris on sound for extraplanetary exploration. So why might we look? This is a picture of Mars. And you might think a microphone would be great because if you ask a panel to be opened or something and you hear that, you know it works well. But if you hear this noise, you know that it didn't work well, it hit something. If we hear this noise, we might say to ourselves, well, it's the sound of a kettle boiling, we know that. But if we hear this noise, if we hear this noise, this is the noise of an ice volcano. Now, we've never recorded an ice volcano, but I wanted to see what it would sound like. So I built one. In fact, built one back in the 70s and recorded the sound of it. So there's all sorts of natural phenomena that might make sound on another world. This is, I'm sorry, my sounds are getting a little. So we've got numerous of the sounds playing at once. Right, this is the sound of lightning on Venus. And this is the sound of dust devils on Mars. So we predicted these things many years ago to try and work out what they would sound like and what we might do if we took a microphone there, how that microphone might be designed. And in fact, we've been lucky enough on Perseverance now that a dust devil passed right over the rover. So you don't have to rely on my simulations anymore. There are real recordings of these things. One of the things I did to try and get people interested in that with Andy is look at humans and how our voice might sound if we went to another world. On Earth, imagine a 5'10" human, like me, who's singing a note of D on Earth. Take us to Mars, and we would actually sound like we were 8'4", singing a very quiet D, the same note. Take us to, and the tallest person, that's not quite as tall as the tallest person ever. Take us to Titan, and we're 9'4", because our brain interprets the sounds that we make in terms of not only the pitch we're talking, but also the size of person we are. And they would sing a loud note slightly lower in pitch. Take us to Venus, and we become very short, sing a very quiet and very, very low note. So we all become bass hobbits on Venus. And I did this to try and get people interested. We did it for free, went around schools, talked to museums around it. And in fact, the Danish Christmas quiz had it as an answer of what would we sound like if we came to another world. So this woman sings a song about Venus, and halfway through we switch her voice to be what it would be were she singing on Venus.
God is on the mountain top, burning like a silver flame. God is beauty, love, Jesus was your name.
Okay, so I hand over to Andy at that point.
Okay. Thank you, Tim. So, hi, I'm Andy Petkulescu from the University of Louisiana at Lafayette. What I want to do is, I have only 2 slides. I want to point out the goals of these sessions. We call it alien acoustics. So the ultimate goal was to try to connect, to build a bridge between the acoustics and the planetary science, and further astronomic communities. So why that? I'm not going to go through all these bullet points. First of all, acoustic sensors are rugged, they're versatile, and oftentimes they do not require extra calibration. So they are a normal choice. We can measure atmospheric structure, the layering of the atmosphere, and composition, low-frequency sounds like infrasound from storms, quakes like Venus quakes, or possibly Titan quakes, volcanoes, lightning, as Tim has shown us by simulations. And also, we can measure, for instance, see the last bullet there, landing zone topography mapping. And this was done by the Huygens lander that had a full acoustic suite of active and passive sensors. So listen only, but also transmit and receive. So Huygens had a sonar with which they were able to map to see the distance to the landing zone as the Huygens probe was descending. Also, my goal is to try to broaden the scope of this collaboration, of this bridge between planetary science and acoustics, to long-duration manned missions, right? We all know that we're going to go to Mars sometime in the near or not so near future. And I have made a list where we can bring all technical committees of acoustics into the fold. Everything from psychoacoustics to musical acoustics to physical to engineering will have a role in long-duration manned missions. And I can answer afterwards if you're curious. And the last slide, this is the history, for now brief, of acoustics and planetary science or astronomy at ASA. In 2007, I organized the first such session in Salt Lake City. Then, together with Tim, we organized that big meeting in 2008 in Paris. These two meetings were focused, of course, around the Huygens landing and the loss of the Mars polar lander that was to have had the first microphone before Huygens. And in 2016, we organized a special issue of JASA on the same topics, which went beyond planetary science a little bit. So that's all I have. Thank you very much.
You can stay up here because we'll have some questions, Tim, if you want to come up too. So I guess I'll start off. So what current missions are underway that have microphones included on them, if any?
We can talk about Dragonfly.
So
Can you
I know that the next mission to Titan, right, will have microphones, Dragonfly, which is supposed to send a octocopter. So Dragonfly is an octocopter. So 4 dual blade rotors, craft on Titan. I think originally it was supposed to have a boat associated with it, but they may have.
I think that was cut from the funding.
Cut from the. Yeah.
The Titan has a thick atmosphere. It's about 1.5 times thicker than our own, so it's a good one for sending a copter to.
Yes.
But of course, it takes 7 years to get there. So it may be the next launched, but it may not be the next one to arrive if they send a Mars microphone after that.
Right.
But Perseverance may last quite a long time on the surface of Mars.
Yes, and it's amazing what they did with the Perseverance mission with the Mars 2020. They have one microphone there, and with this microphone, they basically produced wonders. The data is still coming in, and maybe you know that Mars is acoustically very unfriendly. It has not only a thin atmosphere, but it is composed mainly of CO2, which has a lot of losses, acoustic losses. And they were able to measure the so-called dispersion, the difference, low frequency and high frequency sound speed, from 2 sources. The high frequency from the plasma shock waves that would produce acoustic shock waves from laser breakdown spectroscopy apparatus from as far as 8 meters, and the low frequency from the signals from the helicopter, the Ingenuity helicopter that was flying as far away as 180 and maybe 200 meters. And they were able to detect the sound from the helicopter from 200 meters. That's amazing.
But I mean, to illustrate the power, you would never persuade someone to send an array of microphones covering 2 meters in height and stretching out to 8 meters to Mars. They would take up too much space, too much bandwidth, too much power. Never do it. However, you can fire a laser at a rock 8 meters away, crack it, and from how that crack propagates, as that crack travels to you through the atmosphere, it's collecting all the information about the turbulence, the temperature, all those things that you could never afford to send solid instrumentation, specialist instrumentation to measure. So as it travels to you, it contains all the information, and of course as the sun comes up, over Mars and goes down, it changes as the turbulence and the heating of the ground change. So that you can see the power of the acoustic waves. Instead of sending probes to a place, you're letting the sound wave do the traveling and be your own probe, just as I mentioned at the start of the talk, you could do for Europa, going to the bottom of that vast ocean 100 kilometers away.
And as far as we know, there is a mission in planning, in the planning stage, and is, I think, quasi-approved to send balloons on Venus that will have 1 or 2 infrasound sensors to be carried away by the winds at 50 kilometers.
Yeah, which is really important because the surface of Venus is very hot. It's hot enough to melt lead, and I think the longest a probe has ever lasted on Venus is 3 minutes.
Soviet, yeah.
Something like 3 minutes before they die. But you put it up in the air, I use the word air loosely, and it'll last hopefully quite a bit longer.
And you don't need propulsion. They will be designed to last 100 days, but they will last for more, as we've been told.
Okay. Well, do we have any questions from the audience?
Yes, we have a number of questions. So I'm going to start just by addressing one of them myself. Ben Schwan asked if there will be recordings of this, and the answer is yes. We'll happily provide recordings to media. Just email us at media@aip.org if you'd like that. And also a note about the recordings, they will not contain the lag that anyone might be experiencing on the stream. So if you want some sharper video content, they will be in the recordings. Next question are for you guys. So let's see. Let's see. What microphone technologies are you excited about for using sounds to explore other worlds?
Sorry. Yeah.
I would love to see a microphone that's far from anything else. I think that would be my wish. It's on Mars. Mars has a thin atmosphere, so any solid surface nearby is going to be very, very reflected and complicate the signal. I would love to see a microphone that is far from anything else except 3 other microphones. What I would love is to see microphones 1, 2, 3, 4, because then whatever angle sound is coming at, it would pass through 2, and from the time difference between the 2, you've got the sound speed. It would pass through the others at different times. You've got the direction, but not just the sound, the wind. Normally we have wind covers on Earth. You know, journalists put wind covers over their microphones because they just hate the noise of wind. It's actually quite hard to take wind sensors to other worlds. You know, Mars is dusty. Whirring anemometers would get ground up a bit after a bit. But if you take 3 microphones and the wind blows over one and then blows over another, we can use them to measure the wind speed. And that's something that already, just with the 1 microphone on Mars on Perseverance, the Perseverance team have had really extraordinary skill and luck in kind of teasing out the wind speed. With 4 microphones like that, 1, 2, 3, 4, you have incredible power. So I hope never to see 1 microphone ever go into space. Whenever anybody thinks of sending a microphone, I say, please send 4.
Also, there will be a talk about acoustic anemometry, ultrasonic anemometry, so wind speed measurement on Mars in this session. And there are people who have been developing ultrasonic wind speed sensors with, typically for Earth, they work very well with 6 sensors, 2, 2, and 2, that will measure the entire wind field in 3 dimensions, including small-scale turbulence. And the plan is to send one of these devices on to Mars. And yeah.
And you know, the wind is so important on Mars. It's all there is shaping the planet. It doesn't have water. It doesn't have geothermals that I know of. No, I don't think so. It doesn't have. Yeah, it doesn't. That's what shapes the world. That's what lifts up dust on Mars. So measuring the wind and the turbulence tells you an incredible amount about what you need to do on Mars.
Excellent. Thanks so much. We do have about 4 more, so I'll try and get through these. The next one is from Rick Lovett. He's asking, how well did the sound of the dust devil compare to the simulation?
Actually,
Maybe I can answer that. I haven't had a chance to compare the two, and in fact they're a little different. What I was modelling was if a dust devil is over here, what it would sound like if you were some distance away. Now, Mars eats up, as Andy said, it eats up the sound, it absorbs it. It's a very dead atmosphere. What happened in Mars is the flipping dust devil went right over the rover. So we hear we hear the wind noise, we hear the crackle of particles hitting. That's not sound. Sound is when acoustic energy travels from one place to another at the speed of sound. This wasn't that. So it wasn't this sound traveling as from my voice to the microphone. What it was this. So it was a very different sound source. It was particles hitting the microphone and wind blowing over the microphone. Very different sound source. So I do this, you don't hear it from this distance. So I was modeling a different thing to what they picked up.
That makes sense. And it kind of leads us to our next question from Avery Thompson. What planetary characteristics are involved in affecting sound in other worlds? Is it air density, temperature? Are there other things?
Over to Andy for this.
There is the so-called atmospheric specification, the ambient specification that includes density, pressure, temperature, right? The principal trifecta, but also a big role is played by the composition, by the molecular species that form the atmosphere, and the ratio in which their abundances as a function of height. For instance, on Mars and Venus, we have carbon dioxide mixed with nitrogen, and then some other gases like argon and even water vapor and some other, that we would have to take into account, and our models do take into account various compositions of these molecules.
It's fascinating that we have 2 worlds, Venus and Mars, where the atmosphere is mostly carbon dioxide that absorbs the sound, and also, as we've seen on Venus, has a big greenhouse effect. And then we have 2 worlds, Earth and Titan, where the atmosphere is mostly nitrogen with other stuff in there. So it'd be crazy to say they were the same as each other by a long shot. But they kind of fall into 2 broad camps. And you get Earth and Titan, and sound will travel a long distance without absorption. They're very good acoustic worlds. And you get Venus and Mars, and they're dead worlds. Acoustically, they absorb sound hugely. But they've got these 2 distinct compositions. Then we go to places like the atmospheres of Jupiter, which I'd love to see. I'd love to see a dirigible go to Jupiter and Saturn, and you get a different chemistry again.
I think there is an upcoming mission in the planning stages to send a probe in Saturn through Saturn's atmosphere.
Thank you so much. And I have just a couple more questions, and they're kind of related. Do microphones for space have to have other technical specifications than for Earth? And this question's from Ben Schwann.
So one important characteristic is how much. One important characteristic, rule of thumb, is how sensitive a microphone would be to an incoming pressure signal, an acoustic signal. So, and this is typically measured by the difference between what's called an acoustic impedance. So the air, and I'm using air in a very broad sense, has an acoustic impedance that is much smaller than the impedance of the microphone membrane. And this impedance in air, for instance, is the product between the air density and the speed of sound. And as in electrical circuits, the impedances have to be equal for maximum power transmission. So it depends. If we have a microphone designed for Earth, it will not work as well on Mars, where the air is about 100 times thinner than on Earth. But it may work well on Titan, which has a pressure just 1.5 bars. So, and for Venus, for instance, if we ever plan to go back to landers, we would better design microphones and associated electronics that would withstand 90 atmospheres and 700 degrees Kelvin. So,
interestingly, there are two microphones currently on Mars because there's the Chinese probe. Is that right? Yeah.
Yes.
And that has a very different microphone. That has one that potentially could, it measures displacement, acoustic displacement, so it could be calibrated back to an absolute unit. I think that's important because I think the next big row amongst acousticians will be, what does a decibel mean on another world? Because there's still the people from the underwater world and the atmospheric world still row after a century on Earth about the difference. So we're about to throw in a bunch of other planets, and that's going to be perhaps outside of the world of acoustics it won't matter, but for us it's going to be a very exciting row.
And I guess we'll close with this last question from Christina Milanusik. Can you advise on where one can read more about infrasonic sensors and how they work?
Well, I would advise all papers written for and presented at ASA conferences and in the Journal of the Acoustical Society of America. But for a general audience, there is a book, a pretty thick book, written by one of the authors is Le Pinchon, Pinchon, and it has everything that is known to date about infrasonic monitoring. I don't remember the authors, but we can share it. We can, yeah.
Okay. Yeah, and if you have any more questions, feel free to email media@aip.org, and we can connect you with our presenters. We'll be back in 1 minute with our next presenter.